Codec registry and base classes. Source code lib/codecs.py. This module defines base classes for standard Python codecs, encoders and decoders, and provides access to the internal Python codec registry, which manages the codec and error handling lookup process. Most standard codecs are text encodings, which encode text to bytes and decode bytes to text. But there are also codecs provided that encode text to text and bytes to bytes. Custom codecs may encode and decode between arbitrary types, but some module features are restricted to be used specifically with text encodings or with codecs that encode to bytes. The module defines the following functions for encoding and decoding with any codec. Codecs.encode obj, encoding is equal to UTF, errors is equal to restrict. Encodes object using the codec registry for encoding. Errors may be given to set the desired error handling scheme. The default error handler is strict, meaning that encoding errors raise value error, or a more codec specifies subclass such as Unicode encode error. Refer to codec base classes for more information on codec error handling. Codecs.decode object encoding is equal to UTF-8, errors is equal to strict. Decodes object using the codec registered for encoding. Errors may be given to set the desired error handling scheme. The default error handler is strict, meaning that decoding errors raise value error, or a more codec specific subclass such as Unicode decode error. Refer to codec base classes for more information on codec error handling. The full details for each codec can also be looked up directly. Codecs.lookup encoding looks up the codec info in the Python codec registry and returns a codec info object as defined below. Encodings are first looked up in the registry sketch. If not found, the list of registered search functions is scanned. If no codec info object is found, a lookup error is raised. Otherwise, the codec info object is stored in the cache and returned to the caller. Class codec info encode decode stream reader is equal to none, stream writer is equal to none, incremental encoder is equal to none, incremental decoder is equal to none, name is equal to none. Codec details. When looking up the codec registry, the constructor arguments are stored in attributes of the same name, the name of the encoding. Encode decode, the stateless encoding and decoding functions. These must be functions or methods which have the same interface as the encode and decode methods of codec instances. See codec interface. The functions or methods are expected to work in a stateless mode. Incremental encoder, incremental decoder. Incremental encoder and decoder classes or factory functions. These have to provide the interface defined by the base classes incremental decoder, incremental encoder, and incremental decoder respectively. Incremental codecs can maintain state. Stream writer, stream reader. Stream writer and reader classes or factory functions. These have to provide the interface defined by the base classes stream writer and stream reader respectively. Stream codecs can maintain state. To simplify access to the various codec components, the module provides these additional functions which use lookup for the codec lookup. Codecs.getEncoder encoding. Look up the codec for the given encoding and return its encoder function. Raises the lookup error in case the encoding cannot be found. Codecs.getDecoder encoding. Look up the codec for the given encoding and return its decoder function. Raises a lookup error in case the encoding cannot be found. Codecs.getIncremental encoder encoding. Look up the codec for the given encoding and return its incremental encoder class or factory function. raises a lookup error in case the encoding cannot be found or the codec doesn't support an incremental encoder. Codecs.get incremental decoder decoding. Look up the codec for the given encoding and return its incremental decoder class or factory function. Raises a lookup error in case the encoding cannot be found or the codec doesn't support an incremental decoder. Codecs.getReader encoding. Look up the codec for the given encoding and return its streamReader class or factory function. Raises a lookup error in case the encoding cannot be found. Codecs.getWriter encoding. Look up the codec for the given encoding and return its streamWriter class or factory function. Raises a lookup error in case the encoding cannot be found. Custom codecs are made available by registering a suitable codec search function. Codecs.register search function. Register a codec search function. Search functions are expected to take one argument, being the codec encoding name, all lowercase letters with hyphens and spaces, converted to underscores, and return a codec info object. In case a search function cannot find a given encoding, it should return none. Codecs.unregister search function. Unregister a codec search function and clear the registry cache. If the search function is not registered, do nothing. While the built-in open and associated I/O module are the recommended approach for working with encoded text files, this module provides additional utility functions and classes that allow the use of a wider range of codecs when working with binary files. Codecs.open filename mode is equal to R, encoding is equal to none, errors is equal to strict, buffering is equal to -1. Open an encoded file using the given mode and return an instance of stream reader writer, providing transparent encoding decoding. The default file mode is R, meaning to open the file in read mode. Note, if encoding is not none, then the underlying encoded files are always opened in binary mode. No automatic conversion of \n is done on reading and writing. The mode argument may be any binary mode acceptable to the built-in open function. The B is automatically added. Encoding specifies the encoding which is to be used for the file. Any encoding that encodes to and decodes from bytes is allowed, and the data type supported by the file methods depend on the codec used. Errors may be given to define the error handling. It defaults to strict, which causes a value error to be raised in case an encoding error occurs. Buffering has the same meaning as for the built-in open function. It defaults to -1, which means that the default buffer size will be used. Codecs.encoded file. File encoding is equal to none, errors is equal to strict. Return a stream recorder instance, a wrapped version of file which provides transparent transcoding. The original file is closed when the wrapped version is closed. Data returned to the wrapped file is decoded according to the given data encoding and then returned to the original file as bytes using file encoding. Bytes read from the original file are decoded according to file encoding, and the result is encoded using data encoding. If file encoding is not given, it defaults to data encoding. Errors may be given to define the error handling. It defaults to strict, which causes value error to be as in case an encoding error occurs. Codecs.iter encode. Iterator encoding errors is equal to strict pointer KWRs. Uses an incremental encoder to iteratively encode the input provided by iterator. This function is a generator. The errors argument as well as any other keyword argument is passed through the incremental encoder. This function requires that the codec accept text str objects to encode. Therefore, it does not support bytes to byte encoder such as base 64 underscore codec. Codecs.iterate ITER decode iterator encoding errors is equal to strict pointer args uses an incremental decoder to iteratively decode the input provided by iterator. This function is a generator. The errors argument as well as any other keyword argument is passed through to the incremental decoder. This function requires that the codec accepts bytes objects to decode. Therefore, it does not support text-to-text encoders such as ROT_13, although ROT_13 may be used equivalently with ITER encode. The module also provides the following constants which are useful for reading and writing to the two platform dependent files. Codecs.bom, codecs.bom underscore be, codecs.bom underscore le, codecs.bom underscore utf8, codecs.bom underscore utf16, codecs.bom underscore utf16 underscore be, codecs.bom underscore utf16 underscore le, codecs.bom underscore utf32, codecs.bom underscore utf32 be, codecs.bom underscore utf32 underscore le. These constants define various type byte sequences. Being Unicode byte order marks BOM for several encodings. They are used in UTF-16 and UTF-32 data streams to indicate the byte order used, and in UTF-8 as a Unicode signature. BOM underscore UTF-16 is either BOM underscore UTF-16 BE or BOM underscore UTF-16 underscore LE, depending on the platform's native byte order. BOM is an alias for BOM underscore UTF-16, BOM underscore LE for BOM underscore UTF-16 underscore LE, and BOM underscore BE for BOM underscore UTF-16 underscore BE. The others represent the BOM in UTF-8 and UTF-32 encodings. Codec base classes. The codecs module define a set of base classes which define the interfaces for working with codec objects and can also be used as the basis for custom codec implementations. Each codec has to define 4 interfaces to make it usable as codec in Python: stateless encoder, stateless decoder, stream reader, and stream writer. The stream reader and writers typically reuse the stateless encoder decoder to implement the file protocols. Codecs authors also need to define how the codec will handle encoding and decoding error handlers. To simplify and standardize error handling, codecs may implement different error handling schemes by accepting the error's string argument. German B music dot encode ASCII encoding is equal to ASCII errors is equal to backslash replace. For example, let's run the program. German backslash xdf backslash 266c. German B encode ASCII errors is equal to XML ref replace. The following error handlers can be used with all Python standard encoding codecs. Value meaning strict. Res is Unicode error or a subclass. This is the default implemented in strict errors. Ignore the malformed data and continue without further notice. Implemented in ignore errors. Replace with a replacement marker. On encoding, use question mark ASCII character. On decoding, use question mark U plus FFFT, the official replacement character. Implemented in replace errors. Backslash replace. Replace with backslash escape sequences. On encoding, use hexadecimal form of Unicode code point with formats backslash XHH, backslash UXXXX, backslash capital U XXXXXXXX. On decoding, use hexadecimal form of byte value with format backslash S XHH implemented in backslash replace underscore errors method. Surrogate escape. On decoding, replace byte with individual surrogate code ranging from U plus DC at 0 to U plus DCFF. This code will then be turned back into the same byte when the surrogate escape error handler is used when encoding the data. The following error handlers are only applicable to encoding within text encoding. XML charref replace with XML HTML numeric character reference, which is a decimal form of Unicode code point with format m% hash number. Implemented in XML charref replace errors. Name replace with backslash n dot escape sequences. What appears in the braces is the name property from Unicode character database. Implemented in name replace underscore errors method. In addition, the following error handler is specific to given codecs. Value codecs meaning surrogate pass UTF-8, UTF-16, UTF-32, UTF-16BE, UTF-16LE, UTF-32BE, UTF-32LE. Allow encoding and decoding surrogate code point U plus D800 to U plus DFFF as normal code point. Otherwise, these codecs treat the presence of surrogate code point in str as an error. The set of allowed values can be extended by registering a new named error handler. Codec.register underscore error name error handler. Register the error handling function error handler under the name. The error handler argument will be called during encoding and decoding in case of an error when name is specified as the error's parameter. For encoding, error handler will be called with a Unicode encode error instance which contains information about the location of the error. The error handler must either raise this or a different exception or return a tuple with a replacement for the unencodable part of the input and a position where encoding should continue. The replacement may be either str or bytes. If the replacement is bytes, the encoder will simply copy them into the output buffer. If the replacement is a string, the encoder will encode the replacement. Encoding continues on original input at the specified position. Negative position values will be treated as being relative to the end of the input string. If the resulting position is out of bound, an index error will be raised. Decoding and translating work similarly, except Unicode decode error or Unicode translate error will be passed to the handler, and that the replacement from the error handler will be put into the output directly. Previously registered error handlers, including the standard error handlers, can be looked up by name. Codecs.lookup underscore error name. Return the error handler previously registered under the name. Raises the lookup error in case the handler cannot be found. The following standard error handler are also made available as module level functions. Codecs.strict underscore errors exception implements the strict error handling. Each encoding and decoding error raises a Unicode error. Codecs.ignore errors exception implements the ignore error handling. Malformed data is ignored. Encoding or decoding is continued without further notice. Codecs.replace error exception implements the replace error handling. Substitutes question mark ASCII character for encoding errors or question mark U plus FFFT, the official replacement character for decoding errors. Codecs.backslash replace underscore errors exception implements the backslash ref replace error handling. Malformed data is replaced by a backslash escape sequence. On encoding, use the hexadecimal form of Unicode code point with formats backslash x, hh, backslash u, xxxx, backslash u 3368 times x. On decoding, use the hexadecimal form of byte value with format backslash x, hh. Codecs.xml charref replace underscore errors exception implements the XML charref replace error handling for encoding with text encoding only. The unencodable character is replaced by an appropriate XML HTML numeric character reference, which is a decimal form of Unicode code point with format ampersand hash number. Codecs.name replace underscore errors exception implements the name replace error handling for encoding with text encoding only. The unencodable character is replaced by a backslash n in curly brace dot escape sequence. The set of characters that appear in the braces is the name property from Unicode character database. For example, the German lowercase letter b will be converted to byte sequence backslash and Latin small letter sharp s. Stateless encoding and decoding. The base codec class defines these methods, which also define the function interfaces of the stateless encoder and decoder. Class codecs.codec encode input errors is equal to string encodes the object input and returns a tuple output object length consumed. For instance, text encoding converts a string object to bytes object using a particular character set encoding. Example, CP1252 or ISO 88591. The errors argument defines the error handling to apply. It defaults to strict handling. The method may not store state in codec instance. Use stream writer for codecs which have to keep state in order to make encoding efficient. The encoder must be able to handle zero length input and return an empty object of the output object type in this situation. Decode input errors is equal to strict decodes the object input and returns a tuple output object length consumed. For instance, for a text encoding, decoding converts a bytes object encoded using a particular character set encoding to a string object. For text encodings and bytes to bytes codecs, input must be a bytes object or one which provides the read-only buffer interface. For example, buffer object and memory mapped files. The errors argument defines the error handling to apply. It defaults to strict handling. The method may not store state in the codec instance. Use stream reader for codecs which have to keep state in order to make decoding efficient. The decoder must be able to handle zero length input and return an empty object of the output object type in this situation. Incremental encoding and decoding. The incremental encoder and incremental decoder classes provide the basic interface for incremental encoding and decoding. Encoding or decoding the input is not done with one call to the stateless encoder or decoder function, but with multiple calls to the encode or decode method of the incremental encoder or decoder. The incremental encoder decoder keeps track of the encoding decoding process during method calls. The joined output of calls to the encode decode method is the same as if all the single inputs were joined into one and this input was encoded decoded with the stateless encoder or decoder. Incremental encoder objects. The incremental encoder class is used for encoding an input in multiple steps. It defines the following methods which every incremental encoder must define in order to be compatible with the Python codec registry. Class codecs.incremental encoder errors is equal to strict constructor for incremental encoder instance. All all incremental encoders must provide this constructor interface. They are free to add additional keyword arguments, but only the ones defined here are used by the Python codec registry. The incremental encoder may implement different error handling schemes by providing the errors keyword argument. See error handlers for possible values. The errors argument will be assigned to an attribute of the same name. Assigning to this attribute makes it possible to switch between different error handling strategies during the lifetime of the incremental encoder object. Encode object final is equal to false. Encodes object taking the current state of the encoder into account and returns the resulting encoded object. If this is the last call to encode final must be true. The default is false. Reset. Reset the encoder to the initial state. The output is discarded. Call dot encode object final is equal to true, passing an empty byte or text string if necessary to reset the encoder and to get the output. Get state. Return the current state of the encoder, which must be an integer. The implementation should make sure uh, that 0 is the most common state. States that are more complicated than integers can be converted into an integer by marshalling or pickling the state and encoding the bytes of the resulting string into an integer. Set state. Set the state of the encoder to state. State must be an encoder state returned by get state. Incremental decoder objects. The incremental decoder class is used for decoding an input in multiple steps. It defines the following methods which every incremental decoder must define in order to be compatible with the Python codec registry. Class codecs.incremental decoder errors is equal to strict. Constructor for incremental decoder instance. All incremental decoders must provide this constructor interface. They are free to add additional keyword arguments, but only the ones defined here are used by the Python codec registry. The incremental decoder may implement different error handling schemes by providing the errors keyword argument. See error handlers for possible values. The errors argument will be assigned to an attribute of the same name. Assigning to this attribute makes it possible to switch between different error handling strategies during the lifetime of the incremental decoder object. Decode object final is equal to state. Decodes object taking the current state of the decoder into account and returns the resulting decoded object. If this is the last call to decode, final must be true. The default is false. If final is true, the decoder must decode the input completely and must flush all buffers. If this is not possible, example because of incomplete byte sequences at the end of the input, it must initiate error handling just like in the stateless case which might raise an exception. Reset. Reset the decoder to the initial state. Get state. Return the current state of the decoder. This must be a tuple with two items. The first must be the buffer containing the still undecoded input. The second must be an integer and can be additional state info. The implementation should make sure that 0 is the most common additional state info. If this additional state info is 0, it must be possible to set the decoder to the state which has no input buffered and 0 as the additional state info, so that feeding the previously buffered input to the decoder returns it to the previous state without producing any output. Additional state info that is more complicated than integers can be converted into an integer by marshalling or pickling the info and encoding the bytes of the resulting string into an integer. Set state. Set the state of the decoder to state. State must be a decoder state returned by get state. Stream encoding and decoding. The stream writer and stream reader classes provide generic working interfaces which can be used to implement new encoding submodules very easily. See encodings.utf-8 for an example of how this is done. Stream writer objects. The stream writer class is a subclass of codec and defines the following methods which every stream writer must define in order to be compatible with the Python codec registry. Class codecs.streamWriter. Stream errors is equal to strict. Constructor for a stream writer instance. All stream writers must provide this constructor interface. They are free to add additional keyword arguments, but only the ones defined here are used by Python codec registry. The stream argument must be a file-like object open for writing text or binary data as appropriate for the specified codec. The stream writer may implement different error handling schemes by providing the errors keyword argument. See error handlers. For the standard error handlers, the underlying stream codec may support. The errors argument will be assigned to an attribute of the same name. Assigning to this attribute makes it possible to switch between different error handling strategies during the lifetime of the stream writer object. Write object writes the object's contents encoded to stream. Write lines list write the concatenated iterable of strings to the stream, possibly by reusing the write method. Infinite or very large iterables are not supported. The standard bytes to bytes codec do not support this method. Reset resets the codec buffers used for keeping internal state. Calling this method should ensure that the data on the output is put into a clean state that allows appending of new fresh data without having to rescan the whole stream to recover state. In addition to the above methods, the stream writer must also inherit all other methods and attributes from the underlying stream. Stream reader objects. The stream reader class is a subclass of codec and defines the following methods which every stream reader must define in order to be compatible with the Python codec registry. Class codecs.streamReader. Stream errors is equal to strict. Constructor for stream reader instance. All stream readers must provide this constructor interface. They are free to add additional keyword arguments, but only the ones defined here are used by the Python codec registry. The stream argument must be a file-like object open for reading text or binary data as appropriate for the specific codec. The stream reader may implement different error handling schemes by providing the errors keyword argument. See error handlers. For the standard error handlers the underlying stream codec may support. The errors argument will be assigned to an attribute of the same name. Assigning to this attribute makes it possible to switch between different error handling strategies during the lifetime of the stream reader object. The set of allowed values for errors argument can be extended with register error. Read size is equal to -1, chars is equal to -1, first line is equal to false. Decodes data from the stream and returns the resulting object. The chars argument indicates the number of decoded code points or bytes to return. The read method will never return more data than requested, but it might return less if there is not enough available. The size argument indicates the approximate maximum number of encoded bytes or code points to read for decoding. The decoder can modify this setting as appropriate. The default value -1 indicates to read and decode as much as possible. This parameter is intended to prevent having to decode used files in one step. The first line flag indicates that it would be sufficient to only return the first line if there are decoding errors on later lines. The method should use a greedy read strategy, meaning that it should read as much data as is allowed within the definition of the encoding and the given size. Example, if optional encodings or state markers are available on the stream, these should be read too. Read line size is equal to none, keep ends is equal to true. Read one line from the input stream and return the decoded data. Size, if given, is passed as size argument to the stream's read method. If keep ends is false, line endings will be stripped from the lines returned. Read lines size hint is equal to none, keep ends is equal to true. Read all lines available on the input stream and return them as a list of lines. Line endings are implemented using the codecs decode method and are included in the list entries if keep ends is equal to true. Size hint, if given, is passed as the size argument to the stream's read method. Read resets the codec buffers. Reset the codec buffers used for keeping internal state. Note that no stream repositioning should take place. This method is primarily intended to be able to recover from decoded errors. In addition to the above methods, the stream reader must also inherit all other methods and attributes from the underlying stream. Stream reader writer objects. The stream reader writer is a convenience class that allows wrapping strings which work in both read and write modes. The design is such that one can use the factory functions returned by the lookup function to construct the instance. Class codecs dot stream reader writer stream reader writer errors is equal to string creates a stream reader writer instance. Stream must be a file like object. Reader and writer must be factory functions or classes providing the stream reader and stream writer interface respectively. Error handling is done in the same way as defined for the stream readers and writers. Stream reader writer instances define the combined interfaces of stream reader and stream writer classes. They inherit all other methods and attributes from the underlying stream. Stream recorder objects. The stream recorder translates data from one encoding to another, which is sometimes useful when dealing with different encoding environments. The design is such that one can use the factory functions returned by the lookup function to construct the instance. Class codecs.stream recorder stream encode decode reader writer errors is equal to strict creates a strict stream recorder instance which implements a two-way conversion encode and decode work on the front end. The data visible to code calling read and write while reader and writer work on the back end the data in stream. You can use these objects to do transparent transcodings example from Latin 1 to UTF-8 and back. The stream argument must be a file-like object. The encode and decode arguments must adhere to codecs interface. Reader and writer must be factory functions or classes providing objects of the stream reader and stream writer interface respectively. Error handling is done in the same way as defined for the stream readers and writers. Stream recorder instances define the combined interfaces of stream reader and stream writer classes. They inherit all other methods and attributes from the underlying stream. Encodings and Unicode. Strings are stored internally as sequences of code points in range U plus 000 hyphen U plus 10FFFF. See PEP 3934 3934 more details about the implementation. Once a string object is used outside of CPU and memory, endianness and how these arrays are stored as bytes become an issue. As with other codecs, serializing a string into a sequence of bytes is known as encoding, and recreating the string from the sequence of bytes is known as decoding. There are a variety of different text serialization codecs which are collectively referred to as text encodings. The simplest text encoding, called Latin 1 or ISO 88591, maps the code points 0 to 255 to the bytes 0x0 hyphen 0xFF, which means that a string object that contains code points above U plus 00FF can't be encoded with this codec. Doing so will raise a Unicode and encode error that looks like the following, although the details of the error message may differ. Unicode encode error. Latin 1 codec can't encode character \U1234 in position 3, ordinal not in the range 256. There is another group of encodings, the so-called CARMAP encodings, that choose a different subset of all Unicode code points and how these code points are mapped to the bytes 0x0 hyphen 0xFF. To see how this is done, simply open example encoding /cp1252.py, which is encoding that is used primarily on Windows. There is string constant with 256 characters that shows you which character is mapped to which byte value. All of these encodings can only encode 256 of the 1114112 code points defined in Unicode. A simple and straightforward way that can store each Unicode code point is to store each code point as 4 consecutive bytes. There are two possibilities: store the bytes in big endian or in little endian order. These two encodings are called UTF-32BE UTF-32LE respectively. The disadvantage is that if example you use UTF-32BE on a little endian machine, you will always have to swap bytes on encoding and decoding. UTF-32 avoids this problem. Bytes will always be in natural endianness. When these bytes are read by a CPU with a different endianness, then bytes have to be swapped enough to be able to detect the endianness of a UTF-16 or UTF-32 byte sequence. There is so-called BOM, byte order mark. This is the Unicode character U plus FEFF. This character can be prepended to every UTF-16 or UTF-32 byte sequence. The byte swapped version of this character 0xFFFE is an illegal character that may not appear in Unicode text. So when the first character in a UTF-16 or UTF-32 byte sequence appear to be a U plus FFFE, the bytes have to be swapped on a decodings. Unfortunately, the character U plus FEFF had a second purpose as a zero width no break space, a character that has no width and doesn't allow a word to be split. It can for example be used to give hints to a ligature algorithm. With Unicode 4.0 using U plus FEFF as a zero width no break space has been deprecated with U plus 2060 word joiner, assuming this row. Nevertheless, Unicode software still must be able to handle the U plus FEFF in both roles, as a BOM is devised to determine the storage layout of the encoded bytes and vanishes once the byte sequence has been decoded into a string as a zero width no break space. It's a normal character that will be decoded like any other. There is another encoding that is able to encode the full range of Unicode characters. UTF-8 UTF-8 is an 8-bit encoding, which means there are no issues with byte order in UTF-8. Each byte in UTF-8 byte sequence consists of two parts: marker bits, the most significant bits, and payload bits. The marker bits are a sequence of 0 to 4 1 bits followed by a 0 bit. Unicode characters are encoded like this, with X being payload bits, which when concatenated give the Unicode character. Range encoding U minus 33680 to U minus hyphen 0000007F 0x U this encoding U00080 U00007FF 110XXXXX 10XXXXXX U000000800 U 0000FFFF 1110XXXX 10XXXXXX 10XXXXXX U00010000 U0010FFFF 111110XXX 10XXXXXX 10XXXXXX 10XXXXXX. The least significant bit of the Unicode character is the rightmost X bit. As UTF-8 is an 8-bit encoding, no BOM is required, and any U plus FEFF character in the decoded string, even if it is the first character, is treated as a zero width no break space. Without external information, it is impossible to reliably determine which encoding was used for encoding a string. Each char-map encoding can decode any random byte sequence. However, that is not possible with UTF-8, as UTF-8 byte sequence have a structure that doesn't allow arbitrary byte sequence. To increase the reliability with which a UTF-8 encoding can be detected, Microsoft invented a variant of UTF-8 that Python calls UTF-8 SIG for its Notepad program. Before any of the Unicode characters is returned to the file, a UTF-8 encoded BOM which looks like this as a byte sequence 0xEF, 0xBB, 0xBF is returned, as it is rather improbable that any character encoded file starts with these byte values, which would example map to Latin small letter or with diaries, right pointing double angle quotation mark, inverted question mark. In ISO 88591, this increases the probability that a UTF-8 SIG encoding can be correctly guessed from the byte sequence. So here the BOM is not used to be able to determine the byte order used for generating the byte sequence, but as a signature that helps in guessing the decoding encoding. On encoding, the UTF-8 SIG codec will write 0xEF, 0xBB, 0xBF as the first 3 bytes to the file. On decoding, UTF-8 SIG will skip those 3 bytes if they appear as the first 3 bytes in the file. In UTF-8, the use of the BOM is discouraged and should generally be avoided. Standard encodings. Python comes with a number of codecs built in, either implemented as C functions or with dictionaries as mapping tables. The following table lists the codecs by name together with a few common aliases and the languages for which the encoding is likely used. Neither the list of aliases nor the list of languages is meant to be exhaustive. Notice that spelling alternatives that only differ in case or use a hyphen instead of an underscore are also valid aliases. Therefore, example UTF-8 is a valid alias for the UTF-8 codec. See Python implementation detail. Some common encodings can bypass the codec's lookup machinery to improve performance. These optimization opportunities are only recognized by C Python for a limited set of case insensitive aliases. UTF-8, UTF-8, Latin 1, Latin 1, ISO 88591, ISO 88591, MBCS, Windows only, ASCII, US ASCII, UTF-16, UTF-16, UTF-32, UTF-32, and the same using underscores instead of dashes. Using alternative aliases for these encodings may result in slower execution. Many of the character sets support the same languages. They vary in individual characters where the euro sign is supported or not, and in the assignment of characters to code positions. For the European languages in particular, the following variants typically exist: an ISO 8859 code set, a Microsoft Windows code page, which is typically derived from an 8859 code set but replaces control characters with additional graphic characters, an IBM EBCDIC code page, an IBM PC code page which is ASCII compatible. Codec aliases languages: ASCII 646 US ASCII English, Big 5, Big 5 TWCS, Big 5 traditional Chinese, Big 5 HKSCS, Big 5 HKSCS, HKSCS, CP037, IBM 037, IBM 039, CP273, 273, IBM 273, CS IBM 273, CP424, EBCDIC, CPHE, IBM 423, Hebrew, CP437, 437, IBM 437 English, CP500, EBCDIC, CPBE, EBCDIC, CPCH, IBM 500, Western Europe, CPE 720, Arabic, CP737, Greek, CP775, IBM 775, Baltic languages, CP850, 850, IBM 850, Western Europe, CP852, 852, IBM 852, Central and European, Eastern Europe, CP855, 855, IBM 855, Bulgarian, Byelorussian, Macedonian, Russian, Serbian, CP856, Hebrew, CP857, 857, IBM 857, Turkish, CP858, 858, IBM 858, Western Europe, CP860 IBM 860 Portuguese. CP861 CP is IBM 861 Icelandic. CP862 Hebrew. CP863 IBM 863 Canadian. CP864 IBM 864 Arabian. CP865 IBM 865 Danish Norwegian. CP866 IBM 866 Danish Russian. CP869 CPGR IBM 869 Greek. CP874 Thai. CP875 Greek. CP932 MS Kanji Japanese. CP949 MS949 USC Korean. CP950 CP950. Let's see all the list of, okay, this is a whole list, long list. Okay, 950 MS 95 traditional Chinese. CP1006 Urdu. CP1026 IBM 1026 Turkish. CP1125 IBM 1125 CP86U Ruski. CP1140 IBM 1140 Western Europe, and so forth, like this. EUJIS. Okay, let me scroll through. Okay, then okay, and okay, okay, okay. Python specific encodings. A number of predefined codecs are specific to Python, so their codec names have no meanings outside Python. These are listed in the tables below based on the expected input and output types. Note that while text encodings are the most common use case for codecs, the underlying codec infrastructure supports arbitrary data transforms rather than just text encodings. For asymmetric codecs, the stated meaning describes the encoding direction. Text encoding. The following codecs provide str to bytes encoding and bytes like objects to str decoding, similar to Unicode text encodings. Codec alias meaning. Let's see the list. Okay, so codecs. IDNA. Implement RFC 3490. See also encoding.idna. Only errors is equal to strict is supported. MBCS. ANSI DBCS. Windows only. Encode the operand according to the ANSI code page. OEM. Windows only. Encode the operand according to the OEM code page. Palmos. Encoding of Palm OS 3.5. Punycode. Implement RFC 3492. Stateful codecs are not supported. Row Unicode escape. Latin 1 encoding with \u xxx and \u xxx for other code points. Existing backslashes are not escaped in any way. It is used in Python's pickle protocol. Undefined. Raise an exception for all conversions, even empty string. The error handler is ignored. Unicode escape. Encoding suitable as the contents of a Unicode literal in ASCII encoded Python source code, except that codes are not escaped. Decode from Latin 1 source code. Beware that Python source code actually uses UTF-8 by default. Binary transforms. The following codecs provide binary transforms, bytes like objects to bytes mappings. They are not supported by bytes.decode, which only produces str output. Codec alias meaning encoder decoder. Base 64 underscore codec. Base underscore 64. Convert the operand to multi-line MIME based 64. The result always includes a trailing \n. base 64 encode bytes, base 64 decode bytes. BZ2 underscore codec, BZ2 compress the operand using BZ2, BZ2 compress, BZ2 decompress. Hex underscore codec, hex converts the operand to hexadecimal representation with 2 digits per byte. Binary ASCII dot B to A, binary to A underscore hex, binary ASCII dot A to B underscore hex. Copry underscore codec, copry quoted printable, quoted underscore printable converts the operand to mime quoted printable. Copry dot encode with quotable tabs is equal to true. Copry dot decode. UU underscore codec, UU convert the operand using UU encode. UU dot encode, UU dot and decode, not UU is deprecated. Zlib underscore codec, zip or zlib compress the operand using zlib. Zlib dot compress, zlib dot decompress. In addition to bytes like objects, base 64 underscore codec also accepts ASCII only instances of str for decoding. Text transforms. Text transform. The following codec provides a text transform, a string to string mapping. It is not supported by str.encode, which only produces bytes output. ROT underscore 13, ROT 13 return a Caesar cipher encryption of the operand. Encodings.idna internationalized domain names in applications. This module implements RFC 3490 internationalized domain names in applications and RFC 3492 name prep, a string prep profile for internationalized domain names IDN. It builds upon the punny code encoding and string prep. If you need the IDNA 20008 2008 standard from RFC 5891 and RFC 5895, use the third-party IDNA module. These RFCs together define a protocol to support non-ASCII characters in domain names. A domain name containing non-ASCII characters such as www.aliasfrancais.nu is converted into an ASCII compatible encoding ACE such as www.accent-alias reference alias franais npb.nu. The ACE form of the domain name is then used in all places where arbitrary characters are not allowed by the protocol, such as DNS queries, HTTP host fields, and so on. This conversion is carried out in the application. If possible, invisible to the user, the application should transparently convert Unicode domain labels to IDNA on the wire and convert back ACE labels to Unicode before presenting them to the user. Python supports this conversion in several ways. The IDNA codec performs conversion between Unicode and ACE, separating an input string into labels based on the separator characters defined in section 3.1 of RFC 3490 and converting each label to ACE as required, and conversely separating an input byte string into labels based on the dot separator and converting any ACE labels found into Unicode. Furthermore, the socket module transparently converts Unicode host names to ACE so that applications need not be concerned about converting host names themselves when they pass them to the socket module. On top of that, modules that have host names as function parameters such as http.client and ftplib accept Unicode host names. http.client then also transparently sends an IDNA hostname in the host field if it sends that field at all. When receiving host names from the wire, such as in reverse name lookup, no automatic conversion to Unicode is performed. Applications wishing to present such host names to the user should decode them to Unicode. The module encodings.idna also implements the name prep procedure which performs certain normalizations on host names to achieve case insensitive sensitivity of international domain names and to unify similar characters. The name prep functions can be used directly if they are desired. Encodings.idna.nameprep label. Return the name prepped version of label. The implementation currently assumes query strings, so allowed unassigned is true. Encodings.idna to ASCII label converts a label to ASCII as specified in RFC 3.90. Use STD3A SCII rules is assumed to be false. Encodings.idna to Unicode label convert a label to Unicode as specified in RFC 3490. Encodings.mbcs Windows ANSI code page. This module implements the ANSI code page cp underscore acp availability windows. Encodings.utf8 sig UTF-8 codec with BOM signature. This module implements a variant of the UTF-8 codec on encoding. A UTF-8 encoded BOM will be prepended to the UTF-8 encoding coded bytes. For the stateful encoder, this is only done once on the first write to the byte stream. On decoding, an optional UTF-8 encoded BOM at the start of data will be skipped. Thank you.